Let's see. So this week we're going to learn about several different properties of functions. So far we've really only kind of brushed over the domain and range, but we're going to go into everything in a lot more detail. We're going to talk about the inverse of a function and the difference quotient of a function and all different kinds of function things. But the first thing we need are something called the parent functions. And I kind of threw this word at you last week when we talked about the parabola, but the parent functions are kind of the templates, the most basic version that all other functions kind of come from. And we're going to look at 6 different types of functions right now. So we're going to have 6 different types of functions that we work with in the class, at least for right now. The following pictures we're going to draw are pictures that you need to have memorized. They're not going to be provided to you on a formula sheet or anything. I just expect you to know what these functions look like, okay? And if you don't know them, it's going to make your life very difficult this week when we're trying to work with these functions. So you need to start getting these pictures committed to memory. The first type of function that we're working with in this class is a linear function. So we already talked about that one. I haven't done too much graphing with them yet, but we talked about linear functions. The most basic linear function we can have would be like y equals x. And y equals x looks like a diagonal line straight through the origin. Another name for a linear function is the identity function. Which is going to be important later on this week. So this linear function, y equals x, is also called the identity function. And a linear function is a special case of what more general type of function? Start with the P.
What is the S?
What? I said a linear function is a special case of what more general type of function? Polynomial function. Good. That being the case, what should its domain be?
All real numbers.
Yep, because polynomial functions always have a domain of all real numbers. What would the range for a linear function be?
The Y.
It would go with the y's, and it's also going to be all real numbers because it goes all the way up and all the way down. So both get all real numbers. Alright, so that's one function we've already kind of talked about. We're also going to look at quadratic functions. We already talked about those for a week. So that's like y equals x squared. Looks like a parabola. You already know. You know the domain is also negative infinity to infinity. And the range for this one's 0 to infinity. Alright, we just had a quiz on that. So quadratic functions we have and linear functions we have. Those are 2 of the 6 functions we're working with in class. We're also going to talk about cubic functions.
What is the domain for quadratic?
You tell me. You know. You just answered it on the quiz 4 times. Well, after the quiz is gone. It's all real numbers.
Oh, I remember.
You knew that. Cubic function, of course, would be y equals x cubed. Anyone happen to know what a cubic function looks like? Maybe? Cubic function looks like this. So it's like a piece like that, and then like that, kind of squiggles. That's what a cubic function looks like. A cubic function is also a polynomial function.
That has a multiplicity of 3.
You only refer to multiplicity when you're talking about the solutions to an equation. And if you set x cubed equal to 0, the only answer would be 0, and it would have a multiplicity of 3. But you wouldn't say the function has a multiplicity. Just like multiplicity refers to the answers to an equation. But since this is a polynomial function, the domain is going to be all real numbers. What would the range be for a function like this? Why? Yeah, sure, why not? It goes all the way down, all the way up. So yeah, it uses all the numbers. It's a cubic function. Now, these three functions, linear, quadratic, cubic, those are all polynomial functions. But we also have non-polynomial functions we're going to look at too, like the root function. Are we singing? So root function, y equals square root of x. This one looks like, so it starts at 0, 0, and then jumps out like that. Now, with a root function, notice I'm only using the positive y values, right? I'm not using any negative y values. But when I take a square root of a number, like the square root of 9, that would be plus and minus 3, right? So why do you think with a root function I'm ignoring the negative version of the answer? Yeah, Cam, I just did. Square root of 9 is negative 3. Well, so I can't plug a number inside of the negative, but I'm not talking about the domain right now. I'm talking about the range, the y values, the output of the function. I'm only saying the only outputs I'm using is the positive and not the negatives, even though when we take square roots, we do get negative outputs.
It does include that line?
Well, I mean, it's only going up because that's what I drew it as. Imagine why does it look like that? So remind me, what is a function? What is that thing? All x's go to how many y's?
1.
Yeah, 1 y. Good. You're the first person that has actually answered that correctly on the first try. Rest you need a midterm next week, right? So every x goes to exactly 1 y. But if I chose positive and negative, that x value would go to more than 1 y, which breaks the definition of a function, right? So in order to keep this thing an actual function, that's why we only choose the positive version of things. Okay? Every x goes to only 1 y, so we're just going to ignore the negative output for the function case. What would the domain of this function be?
0 to infinity.
Correct. Good. And then the range?
0 to infinity.
Same thing. Very good. So it starts at 0 and goes up. I gotta say, y'all are a quieter class than my other class, but at least when you answer the questions, you answer them correctly. Good. So that's 4 of the parent functions. Here's another one. We kind of mentioned this one before, a rational function. Y equals 1 over x. I think we talked about that before when we talked about function notation. This is called a hyperbola graphically. I know it's hot, I'm sorry. I told them this morning and they said the AC person was supposed to come in the afternoon. And it's afternoon, I don't see nobody. Anyone happen to know what 1 over x looks like graphically? Hyperbola? So what this one looks like is like there's a piece in this quadrant. It won't ever touch the 0. It has these things called asymptotes. So the y-axis and the x-axis for hyperbola serve as asymptotes. Maybe you've heard that word before?
Yes.
So an asymptote means a line that the function approaches but never crosses. So as the pink part goes over and over and over and over and over, it will never get crossed across this blue dotted line. Same thing on this side. The pink will approach the blue dotted line, but it'll never cross it.
So what did you say the asymptote was?
For the parent function, the asymptotes are the x and y axis, but it could be shifted somewhere. We'll talk about. But all asymptotes means is a line that the function approaches but doesn't cross. Do y'all remember what the domain for a function like this would look like? We did it before. A couple weeks ago. And what's in between them? Yeah, good. Because the only number that we can't use is 0, because you can't divide by 0. But every other number is okay, so we union those two intervals together. How about the range for something like this? What's the only y value that's not used?
So you don't have to put a bracket next to 0?
No, in fact, you shouldn't use a bracket, because we're trying to not, we don't want to use the number 0. We're trying to exclude it. The range is going to be the same thing. 0 is also not used for the range. It goes all the way down to negative infinity, all the way up to positive infinity, but 0 is not used. So negative infinity to 0, union 0 to infinity. And then last parent function we have is the absolute value function. This is y equals absolute value of x. And we kind of talked about that a little bit before. Remember that was the one that was defined in a piecewise way. And remember when you have the equations that you're solving, you have to break it up into the two cases, the positive and negative, right? Graphically, as a function, this one looks like a v. It's not a polynomial function, but the domain is still all real numbers. I can plug in any number I want to absolute value. And I'm not going to be dividing by 0 or taking the square root of a negative. What would the range be?
0.
Is that 0 going to have a bracket on it? Yeah, it will. Because it equals 0 right there. Good. So, all these pictures are pictures you definitely want to have committed to memory because you're going to. I'm never going to ask you or require you to graph anything, but I feel the problems are pretty impossible to do unless you at least have the picture in your head of what these things look like. So you need to know when we're talking about absolute value, it looks like a v, or all these other functions. You need to know what hyperbolas look like and root functions and stuff. I will not be providing you a formula sheet with these pictures, so you have to make sure you remember those. Absolute value. Hyperbola. It's like hyperbola. But when you say it, it's hyperbola. Not hyperbole. That's a English thing. What's a hyperbole?
An exaggeration.
Oh, y'all know that, but you don't know what hyperbola. It's almost the same word. Did you just say my handwriting is ugly? Well, I apologize. All right. So last week we talked about transformations for quadratic functions, right? We talked about shifting them and flipping them and stuff, and you just had it on a quiz. Oh, yeah.
Did you say number 6 is a hyperbola?
No, she was asking how to spell hyperbola. This is hyperbola. I just have ugly handwriting, apparently. That's how y'all... when I was in high school, I was a lab assistant for the department chair of science. And she was always at meetings during my period for chemistry. And so since I was a lab assistant, I would sometimes get to lecture. But since I was just a high school student...
High school?
Yep. But since I was just a high school student, I couldn't actually teach the class, so they still had a sub in there for me. And I was up on the board. We were doing Hess's Law or something, or balancing equations. I forget what we were learning. But I was writing on the board, and I drew a 4. And the sub teacher, he didn't know chemistry. He didn't know what the hell he was talking about. But he stopped me in the middle of my lecture and wrote up to the board. He was like, when I draw my 4s, I draw them like this, and I guess sometimes they look like Y's. And he was like, son, no, you're doing it wrong. And he told me to draw my 4s like this. And he just sat back down. And it's haunted me to this day that I can't draw 4s correctly.
That's how I draw my 4s. How the sub did.
Like that? What's wrong with that? I was just so embarrassed because back in the day I wasn't the extreme, fantastic public speaker I am today. And I was so embarrassed, and I was like, this jerk who doesn't even know chemistry trying to tell me how to teach the... Anyway. I'm sorry you couldn't read my handwriting, though. What were we talking about? Quadratic functions. So we talked about shifting them and the function transformations that go with that, but it turns out those transformations apply to all the functions we just wrote down. So the same rules we had for shifting right and up and going upside down applies to every picture we just had. So those are the function transformations. So just like with parabolas, if I have a number on the inside of the function, that's going to move it left and right, right? A horizontal shift. So as we go left or right, and it goes opposite of the sign, right? So it's a little bit different though, because like with quadratic, so it's just whatever number is inside the parentheses. But now it could be inside of the square root, or inside the absolute value bars, or inside the denominator, or inside whatever. As long as it's inside the function, that means it's moving left and right, but opposite of the sign. And likewise, if I have a number on the outside of the function, that's going to move it up and down, a vertical shift. So that's going to go up and down, but the same direction as the sign. And let's see, we also had a rule that if there was a negative in front, then that's going to flip it upside down, be a vertical reflection. So it's just going to flip upside down. And then a new one we can talk about now, if you have a negative on the inside of the function, if the x is multiplied by a negative, it's going to be a horizontal reflection. Or it's going to flip sideways. We didn't talk about that before because if you flip a parabola sideways, it doesn't really matter, right? It's the same kind of image. But these are the important function transformation rules. It's the exact same things we had with quadratic functions. There are other function transformation rules that you might have heard about before or read in the book or something. If you have a number times a function, like a times f of x, that's a vertical or a horizontal stretch or compression. But I don't really care about that one because it doesn't actually affect any properties of the function. It just changes what the picture looks like. Depending on that number, it can make the picture wider or skinnier or something. But none of the important properties of function are going to change based on that. So I don't find it very important. But the book seems to care a lot about it for some reason. It's just a cosmetic change. These are the important ones. So horizontal shift, and vertical and horizontal reflections. For example, say that f of x is the absolute value of x plus 2 minus 8. How is that one going to shift?
Vertical reflection?
No, there's no negative in front.
Oh, horizontal shift?
How?
Right two, left two.
Left 2, opposite of the sign, right? So left 2 and down 8. Same thing as a parabola, except it's absolute value this time. So left 2 and down 8. And it's going to look like a V, right? Something like that. Again, your pictures don't have to be super detailed or anything, as long as you get the idea of what the function kind of looks like. What would the domain be? Yep. I don't know if you noticed, but the only functions we've talked about so far that don't have a domain of all real numbers were the square root and the hyperbola. But the linear, quadratic, cubic, and absolute value all had a domain of all real numbers. What would the range be for this one?
Bracket.
Yeah, that's right. Starting at negative 8 and going up to infinity. Good. So,
How'd you get that for the range?
remember the range goes for the y values, so since the lowest y value is negative 8, otherwise the graph is going up. be from -8 to infinity. Very, very similar to what we did with parabolas already.
All we need to find.
For right now, it is. By the end of the week, so what we're building up to is I'm gonna give you like a single function, and then ask you like 20 questions about it. So, well, lots of stuff, but we're gonna learn more than domain and range. What if I had f of x is the square root of x minus 1 plus 3? How is that one going to shift?
Horizontal or so.
You're right, up 3
Right.
and right 1, yeah. Right 1, up 3. The only time it's going to have a reflection is if there's multiplied by a negative somewhere. And then since this is a square root function, it's going to look something like that. What would the domain be? What x values are being used?
So like from the whenever you're doing the square root function, there I guess you said I guess the vertex. There's only one. It only goes one way from the vertex.
Yeah, it does.
1 to infinity.
Uh-huh. And it'll always look like that,
So
yeah.
it'll never go back.
It could be reflected in some way. We'll look at in a minute. But it's only going to go one direction, yeah. And you're right, it's going to go 1 to infinity. Because that's the x values that are being used. How about the range? Yeah, good. 3 to infinity. Both with brackets, because it equals it there. Alright, what if I had f of x is, I don't know, 1 over x minus 4 plus 1. When you're graphing one of these hyperbolas, one of these rational functions, I would recommend that you first graph the asymptotes and then graph the curvy pieces to it. So the asymptotes are going to shift to right 4 and up 1, like the grid lines. So that's going to be there. And then you can draw the actual hyperbola itself in each little space it's supposed to go in. So there's the first piece approaching those asymptotes, and then the second piece, again approaching the asymptotes that you draw. That's probably the easiest way to do it. Start with the asymptotes and then fill in what's supposed to go where. What would the domain for this one be? What's the only x value that you can't use? Can't divide by 0, but what's going to give me 0? 4, right? So 4 is the only x value I can't use because it results in 0. So the domain is going to be -infinity to 4, union 4 to infinity. What about the range? What's the only y value I'm not using?
So I have a why do you think that it can't touch 4?
Why you can't touch 4 right here? Because you can't plug in 4. You can't divide by 0.
The range would be -infinity to 4.
Nope, 4 is an x value. 1, yeah. The 1 is the y value that's not being used. So it'd be -infinity to 1, union 1 to infinity. Whew, yeah. Okay. So hopefully, new pictures, but the exact same thing we did last week as far as shifting things. So make sure you're getting those pictures committed to memory. The next property of functions we're going to talk about is intervals of increasing and decreasing. Okay, so this is actually kind of tricky, but here's some notes to think about. When you're doing intervals of increasing and decreasing, you always move from left to right. When you're looking at your graph, you always go from left to right. And further, intervals of increasing and decreasing are along the x-axis. Okay, so it's kind of tricky. So we could define increasing and decreasing mathematically. There's mathematical ways to define it. But for us, well, let's think increasing means you're going up. Decreasing means you're going down. Easy enough. But to figure that out, you're looking at y values, seeing if the y values are going up or the y values are going down. The reason it's tricky is your answer is actually along the x-axis. You're answering the question, at what x values are the y values increasing? Or, at what x values are the y values decreasing? But your answer is going to be on the x-axis. You're looking at two different places at once. And lastly, you want to always use parentheses. And never will you have a bracket in your intervals of increasing and decreasing. The reason is, at a specific point, you can't be increasing or decreasing. Imagine like a single frame of a cartoon, nothing's moving. But once you have a range of values, things can move around, increase or decrease. So we can never include a bracket, we can never use a specific point for an interval of increasing and decreasing. So here's what I mean. Say you have like, I don't know, y equals x squared, parabola. Looking at this picture, does it look like the graph is always going up?
Yes.
Yeah, most people say yeah. The reason it's not always going up is because you have to go from left to right along the graph. So as you go from left to right, the graph is actually going down and then up. Right? So it's like it doesn't matter which way you draw the graph or what way your arrows are pointing or anything. It's as you go from left to right on the x-axis, how does the function look? Right? And the function's going down this part and then up. Okay? So if we're looking for intervals of increasing and decreasing, this is the part where it's going up, right? This part of the graph corresponds to this part of the x-axis. So from 0 to infinity is where the graph is increasing. This part of the graph is where it's going down. And it corresponds to this part of the x-axis. That'd be negative infinity to 0. And then that's it. And make sure you're only using parentheses. Your answers are on the x-axis, and you're careful to go from left to right across the picture. So let's go back and look at this absolute value one we did. Where would that one be increasing, and where would it be decreasing in it? What do you think? Where is that graph increasing? So negative 8 is a y value, though. Remember, it has to be on the x-axis. So this part is where it's increasing. That corresponds with that section of the number line, right? So it'd be from negative 2 to infinity. No, you don't put a bracket. It's parentheses. Did I put a bracket on those? No. Oh. With increasing and decreasing, you can never put a bracket anywhere. It will never have a bracket. What would the decreasing part be?
Negative infinity, negative 2.
Yeah, negative infinity to negative 2. So negative infinity up to there is where the graph's going down. As you go from left to right. Okay. Again, it doesn't matter. Like even though when you draw this picture, you probably just go up and up, so you just think it's always going up. As you go from left to right, it's not actually doing that. How about this square root function we did? Where is it increasing and where is it decreasing? So what now? Yeah, it'd be 1 to infinity. Because from this point forward, the graph's going up. Where is it decreasing? Well, is there even a negative infinity to use? So where is it decreasing? The number 0? The point 0?
At the vertex, and it's like decreasing.
Really? Y'all getting creative. Does this graph go down?
No.
No, it's not decreasing. So to write that down, you can either put that symbol down for the empty set, or that symbol for the null set. But yeah, it's not decreasing. I was expecting someone to tell me it wasn't. Oh, too shy. A function that always increases or always decreases is called monotonic. What is Siri trying to connect to exactly? Monotonic means it's always increasing or always decreasing. Okay? You know, like monotone, always the same, always doing the same thing. So it's always increasing or always decreasing. So with that absolute value function we had, would that be monotonic?
Yeah.
No, it's
The
not.
last two.
This, yeah, the absolute value function, yeah, this is not monotonic because sometimes it's decreasing and sometimes it's increasing. But this one we just did, it is monotonic. It's always increasing. Okay, let's look at this hyperbola. Where is that one increasing and decreasing? So let's do increasing first. Where is the function increasing?
It doesn't.
Correct, it does not increase. Yeah, so as you go from left to right, this part's going down, and then this part's still going down. So it does not increase. Where does it decrease then? Like negative infinity to infinity?
Yes.
No.
Or infinity, it's a negative.
No, that's just backwards.
At 4.
You still can't use the number 4. So for decreasing, it's going to be decreasing everywhere, but along its domain. So the decreasing is going to be the same as the domain.
Okay.
So make sure, even when you're doing intervals of increasing and decreasing, you have to make sure you're not actually dividing by 0 or something. Okay, so what page is this? 4? Let's look at an example of what would make a really good midterm question, at least for right now. So say I gave you f of x is negative x squared plus 2x minus 3. And I want to know the domain and the range and the intervals of increasing and decreasing, and that's all we have talked about so far. But we'll add to that list as we go. This one should be pretty easy because it's quadratic, so we've already done it. Yeah, now you know, right? Yeah, domain is all real numbers because it's polynomial. All quadratic functions have that domain. To answer the rest of these questions, though, we really need to know what the picture looks like. So, well, where's it going to go, though? Okay, where on the graph? You have to complete this square first to get it in vertex form, right? So how can I do that? Got to take the negative out. And then I got to add in the blank space. What's going to go in the blank space, the first one? 1 is going to go in. You have to take half of it and square it. So half of 2 is 1, and 1 squared is 1. What's going to go in that blank space? How come it's negative 1? Because the negative outside. Good. Yeah, that negative times that blank gave you that blank. All right, y'all are getting that down pretty good. That's going to factor into x minus 1 squared. And then what's that going to simplify to? -2. Yeah. So we know this shifts right 1, down 2, and opens upside down. What would the range be?
Infinity to -2.
Negative infinity.
Negative to -2.
Yeah. Negative infinity to -2. Where is the function increasing?
Negative infinity
To
to
1, on the x-axis. So this part of the x-axis corresponds with that part of the graph that's going up. So it'd be negative infinity to 1. Make sure you're using parentheses on those. Where is it decreasing then?
1 to
Nope. Positive infinity, right? Is the function monotonic? No, because it's doing increasing and decreasing. Good. So that's kind of what we're building up to. Like, here's a single function, do this, all this stuff. All the function stuff. Let's get through a little bit more and we'll call it a day. It's so hot in here.
so hard.
Let's look at those reflections a little bit closer. So we talked about horizontal and vertical reflections. So say we have f of x is the square root of x. That's just a regular parent function. It's going to look like that. Let's look at negative square root of x and square root of negative x. If the negative is on the outside of the function, that's going to flip the picture upside down. So which quadrant would that picture be in if I flip it upside down? The first, second, third, or fourth? The fourth, yeah. If I take that and flip it upside down, so we go down here. If the negative is on the inside of the function like that, it's going to flip it sideways, flip it horizontally. The second quadrant, yeah, so it's going to go like that. Okay. So Victor, I think you were asking this earlier. Maybe it does always go one direction, but it could flip around some way. Now some of you will be like, oh my God, you told us several times you can't have a negative inside the square root, and you're right, I did say that. But look at this, what's the domain for that function? Negative infinity to 0, right? Using the negative x values. And if I plug in a negative number for x, what's going to happen inside? It's going to turn to a positive because the two negatives will cancel out. Okay, so as long as the end result inside is not negative, it's going to be okay, which is why we're only using the negative x values here. Now, all this flipping around and stuff kind of alludes to different types of symmetry that functions can have. Like a parabola, if you flip it sideways, it's going to be the same thing, right? So that's what we're going to talk about next, the symmetry of functions. Okay, there's two types of functions as far as symmetry is concerned, even and odd functions. So even functions, so a function is even if and only if. That's what if with two f's means. If and only if. So function's even if and only if f of x equals f of negative x. Okay, this is the algebraic definition for an even function. And even functions are symmetric with respect to the y-axis. And a good example of an even function would be like y equals x squared, which you can remember because 2 is an even number. So y equals x squared looks like a parabola, and that's symmetric with respect to the y-axis. You know, flip it sideways and end up with the same thing. But this is like, if I ask you to show something's even, you can't just draw a picture, you have to actually use this definition. I'll tell you how in a second. That's even. You can also have an odd function. So a function is odd if and only if f of negative x equals negative f of x. And that's the algebraic definition for an odd function. And odd functions are symmetric with respect to the origin. So a good example of that would be y equals x cubed. And you can remember that because 3 is odd. So the cubic function looks like this. When I say symmetric with respect to the origin, I mean if you flip it both ways. So can you imagine in your head, like if I took that and flipped it upside down and took the result and flipped it sideways, I'd be back to where I started? Can you imagine doing that in your head? That's what symmetric to the origin means. You flip it both ways. F of negative x equals negative f of x. Both of those boxes are probably the important things you want to know. And both of these are special types of symmetry that functions can have. So in addition to saying what's the domain and range and increasing and decreasing and stuff, I can now ask you what is the symmetry of the function. Is the function even or odd or neither? So, for example, I could say, let's look at f of x is x squared plus 3. And I want to know, is it even, odd, or neither? Okay, here's how I think you should figure something like this out. What I would do is I would write out 3 functions. F of x, f of negative x, and negative f of x. Okay, what we're going to do is we're going to figure these functions out, simplify them. If the top ones are the same, that means the function's even, because that was the definition of even, right? And if the bottom 2 are the same, that means the function's odd, because that's the definition of odd. So that's what we're going to do. We're going to figure out what these functions are, simplify them, and compare. And as long as something matches up, it's going to be even or odd. It might be the case that nothing matches up, in which case it just doesn't have symmetry. It's nothing. But let's see. So f of x, that's the original function, x squared plus 3. What does an f of negative x mean to do? Like, how can I figure that out? Yeah, that's right. That's what it means. So you take that and plug it in for the x. So it's going to be negative x squared plus 3. And obviously, when you square a negative, it's going to cancel out and go away. So that's x squared plus 3. Now, right away, since those two are the same, that means the function is going to be even. Okay, when you compare them, as long as they're the exact same thing, that means it's going to be even. If we did finish this one out, though, the negative f of x means you take a negative and distribute it to the entire original function. So negative and then parentheses, whatever the original function was. That'll distribute and give you negative x squared minus 3. Which obviously isn't the same as those, but since those two match up, it means the function is even. If the bottom two matched up, it would mean the function's odd. And then if nothing matches up, it means you either made a mistake or it just doesn't have any symmetry.
You said the bottom 2 match up with odd?
Yeah, so if these two match up, then it's odd. Because that was like the definition of odd.
So it has to match up, it can't do by itself.
Yeah, you have to figure out all 3 of these things still, but you compare these two instead. Let's stop here for the day, because I'm sweaty and gross. And we will continue talking about this stuff tomorrow. Don't forget there's homework due tonight. Please don't get a 0 because you forgot the homework. And, yeah, I'll see you tomorrow.